Now with the introduction. So first of all, I want to inform you this session will be recorded and will be available afterwards on our EU Tech Talk website. Welcome to today's webinar in our EU Tech Talk series. Today's presenter is Francesco Garutti. Francesco is the Product Marketing Manager for Alta Products located in Italy. He is working now in Alta since 2010, and he has a lot of experience in all the products, all applications around these products. He's working after Alta is developing and manufacturing microwave generators and systems for all the different applications, including food and beverage packaging, environmental and advanced industrial processes, as there are coating, material growth, and automotive, and of course, vacuum drying, which is the topic of today's talk. Francesco, the stage is yours.
Yeah, thank you, Bruno. So let me share my screen. Let me know if you can see the presentation.
Yep, excellent.
Okay, so as Bruno was mentioning, during this tech talk, we will try to give you a picture of the microwave vacuum drying process. So we will talk about why using microwaves, the technical challenges we have to face using microwave together with vacuum especially, and the possible solutions. So the purpose of microwave drying for batch processes is in general to extract water from products by keeping its temperature under control, usually below a specific value. This approach is specifically targeted in several occasions. For example, in any moment when the process requires a lower boiling point of water or a lower pressure, for example, or simply because traditional heating can't be used, or when it is required to selectively heat dielectric material, such as water, for example, faster compared to traditional heating. Or again, when process involves ingredients which are sensitive to temperature, which can't be processed, so heated, over a specific temperature level in order to preserve their quality and texture. For example, food industry, some new flavors, some new ingredients, which over a specific temperature can be damaged. Chemical industry, same topic. Some chemical reactions to be kept below or within a specific range of temperature and pressure. Or last but not the least, we use microwave vacuum drying system when it is mandatory to reduce process time to avoid overstressing the material to be heated, or simply because I didn't put it here, but maybe simply because we want to increase the throughput. In all these circumstances, even though traditional heating is cheaper, at least on a system level, it can't offer the level of performances desired in terms of speed, quality, and efficiency. So let's say there are two main approaches we are describing now today. The first one is using constant pressure and temperature, the so-called continuous heating. And the second one is variable pressure and temperature, so-called discontinuous heating. The first one is the most used method and allows normally to work safely with minimal residual pressure of 100 millibar. This level of pressure is safe, and I will describe what safe means, because regardless of the gas fluid involved, the risk of arching is limited. So when I say safe, it means that we are avoiding arching. The method is based upon a calculation of the total power requested to dry a specific quantity of water in a specific time, or vice versa. With the given power available, it will result in a specific drying time for the same amount of water. So, to make a summary, given amount of water to be dried means a given amount of power available, and this means a water boiling temperature at roughly 46 degrees at 100 millibar roughly, and this results in a specific drying time. The second method is let's say playing with pressure and temperature. So if for a specific reason the boiling temperature of the water is below 30 degrees Celsius, or at least the target is below this value, this method can be preferred. Or if for any reason the dryer can't be too big. This method is composed by two alternate phases, playing with microwave power and pressure alternatively. More in specific, there will be a first stage when we could stay at 100 millibar using microwave to make the product reach the boiling temperature. So similar to the first step, and then stop microwave and decrease pressure as fast as possible to keep water evaporating below the threshold desired, using the energy which is stored during the first step. So let me quickly describe you the challenges we have to face dealing with the microwave and vacuum. Let me describe you the facts. Facts are that the lower is the boiling temperature which you desire, or which the process need, the lower is the pressure the system has to operate. But the lower is the pressure, then the lower is the maximum electrical field you can apply, incurring ionization, so arching of the dryer internal atmosphere. So what happens? It happens that the moment you go down with pressure within the cavity, you have water vapor, and this water vapor can be ignited if you exceed with the electrical field. Why electrical field? Because the microwave are in any sense an electromagnetic source. So the moment you are applying microwave, you are applying an electromagnetic field inside the cavity. So at the very end, the lower is the boiling temperature desired, the lower is the microwave power which can be used. In any case, as I said, we have to avoid bypassing the air breakdown voltage level of gases. This value is strictly linked to pressure and frequency of the electromagnetic field. Just to give you some numbers, we are dealing with ISM band, so 950 megahertz or 2450 megahertz. And for example, in a region of vapor pressure of 100 millibar, so which is roughly 75 torr, we have a limit of 1000 volt per centimeter, or 100,000 volt per meter. Please remember this number, okay? So we have to be careful not to exceed this value. Otherwise, we will have air breakdown voltage. So fact number 2, close to ambient pressure, so no vacuum, in a typical WR340 waveguide, we can reach this level of electrical field. For a 10 kilowatt microwave source, we are close to 80,000 volt per meter. Okay, remember the 100,000. And for a 6 kilowatt microwave source, 59.2. Let me open and clarify. The WR340 is a typical dimension of waveguide. It is also called R26, so it means 3.4 inch times 1.7 inch, or in millimeter, it is a waveguide of 86 millimeter times 43 millimeters. Okay. Okay, this is the typical waveguide we use from 1 kilowatt up to 10 kilowatt microwave generators. So we are reaching this kind of electrical field. So as you can see, when we are dealing with region 3 process area, we are already too close to corona type breakdown events. So at the end, what to do? What can we do? Or how can we approach these technical challenges? So I summarized mainly five things to look at. The first thing is to change the dielectric of the pressure windows. So we are dealing with pressure, so for sure we will have a pressure window. This pressure window can be quartz, alumina, Teflon, which means PTFE, anything which is transparent to microwave, and which has an effect on the electrical field on the low pressure side of the cavity by reducing or changing the impedance jump from ambient pressure to vacuum. Honestly, most of the time this is not enough. This is more process related. So let's say we are dealing with food companies very often don't like quartz or alumina. They prefer Teflon. So it's more process related than actually solving the problem of air breakdown. Then, two very important things, changing the geometry of waveguide of the microwave launcher and change the geometry of the cavity. So basically, to say it in other words, how microwave is entering the cavity and how the cavity is made. Here you can see a couple of examples of simulation. Of course, the scale is not visible enough, but you have to take into consideration the fact to change the way you are entering inside the cavity and the geometry of the cavity itself. In my point of view, in our point of view, this is one of the most important things to look at least on a design level. Then hopefully you can see this. So another thing to look at is simply the power reduction. So let's say that decent level of performances can be also reached by playing with the power level of microwave sources. For example, if you think to decrease the microwave power according to the recipe or acting on the duty cycle of the microwave generator, probably the result is good enough to create an efficient process. Why I'm telling you this? Because at the very end, we have to avoid the stationary wave, which creates high electrical field areas inside the applicator. The stationary wave is created when there is interference between forward and reflected power. So in any case, we have to avoid or minimize the creation of this stationary wave. And this means to minimize reflections. Reflection rise when impedance change occurs. To limit impedance change is very difficult or impossible in a transformation process because most of the time the process is changing his dielectrical properties during the process itself. But acting on power partialization or power reduction can help minimize the reflection effect. So this is maybe a simple thing to do, but it can be really effective. Then, last but not the least, very specific attention has to be taken into the cavity design and maintenance to avoid potential sources of internal arching. So, for example, no one of the following are good manufacturing practice, as I say. For example, if you have poor maintenance of the system or incorrect component design, of course, you can occur into arching inside the cavity, even though if you did a good design, for example, but the system is not correctly cleaned, especially when we talk about choke or critical parts like gaskets and so on. This can lead to discharge. Or if you have an incorrect component design, so sharp items inside the cavity, pointed metallic parts like screws, edges, and so on, and bad electrical contact, which are the result of bad tolerances or different finishing between materials. All these can be the source of potential internal arching. So if I was, let's say, if I need to give you a priority, of course, I would say the most effective thing is to start from here. So the moment we have to help a customer to design a cavity or to make to assist him while developing his own cavity, we focus immediately on how the microwave are entering inside the cavity, and second, how the cavity is designed, because these two things can immediately tell you if your process is at risk in terms of arching. Of course, risk is a word that no one would like to listen. At the moment, please focus on the word risk in terms of losing a batch. But you know, sometimes the batch can be very valuable. So we don't want to lose batch. So I would give priority to this. And as a second thing, I would try, I would follow a trial and error process to understand where we can highlight potential weakness of the system, potential bad tolerances, or potential area where the electrical contact is not guaranteed, or again, potential area where we can have in the future some consumption. So in this specific example, there was a process in batch which required opening and closing of a window, of a pressure window, to check periodically the product. So in this case, what you see here is a microwave gasket. So this part guarantee that the electrical contact is done through all the window, and of course avoid microwave leakage. Opening and closing this door continuously, of course, has an effect on the consumable material, and this can be considered as a consumable material. Of course, you can have different type of gaskets with the so-called fingers, any type of other gaskets are available, but sooner or later these parts have to be checked and replaced, for example. Or always looking at this slide, the same application had a rotating chamber, so a rotating cylinder. So basically, the design was made in order to guarantee zero microwave leakage, even though there was no electrical contact on the cylinder and the external structure. So these are called microwave choke. So there is a specific design which allow you to guarantee zero leakage, even if two parts are not perfectly electrically connected. This is the same design everybody of us has in his own microwave oven. So inside the door, the front door, which is not visible, you will have a design like this. So imagine this as a microwave door, and this is the gasket, not the gasket, it's the choke which prevent microwave to exit. But if the process is particularly dirty, so let's say it's full of dust and small particles, this sooner or later will enter into this and will result in an arching, because this will prevent the choke to do his job. So it is very, very, very important to clean and to periodically inspect chokes and gaskets. Okay. Then I put here a very stupid detail of a simple screw which was inside a vacuum chamber. No one noticed it until it started sparking. So, of course, the moment you are entering inside a cavity with very high level of pressure, so very low level of pressure, you have to guarantee that electrical contact is absolutely perfect. Another example was, for example, the contact of an aluminum surface with a stainless steel surface. These two components were made with different technologies. So one, the aluminum part was machined, the other was welded. So there was not the same level of polishing, let's say, between the two materials. And this led to discharges. So many small things, but all of them are important. Of course, following this, so the moment you have designed and let's say taken into consideration how to enter correctly inside your cavity, the moment you have designed a good cavity and eliminated all the possible sources of arching, then you have to work on the process. So if you have I don't know, 10 kilowatt or 50 kilowatt of microwave inside your cavity, this doesn't mean that you have to use all the time 50 kilowatt or all the time 10 kilowatt. You can use at the beginning 10 kilowatt, then reduce, or you can use 10 kilowatt for a couple of minutes, then stop, and then start again, and so on and so on. So this is a way that is process related to increase the efficiency of the process and also avoiding arching. This is also important because let's say to play with the power, because arching itself can be stopped only if the microwave is stopped. So the moment you are experiencing arching inside the cavity, the fact to have let's say a duty cycle is preventing you to have a continuous plasma inside the chamber, and it is a way to stop plasma occurred inside the cavity. So, but there are not just bad news. Let's say that good manufacturing practices are possible. We experienced different processes or development and assisted several customers. And all of this could lead to very good result. In the following example, this is a test I made. This was a pretty big, in my opinion, tank. It was roughly 6 meter long with a diameter of 9 meter. We reached successfully 100 kilowatt, roughly at 80 millibar. Okay, so at 80 millibar, we were able to reach 100 kilowatt at 2450 with 10 sources of 10 kilowatt each, without arching discharges. Then the moment we went below this threshold, we had to decrease the power level in order to avoid absolutely arching. This was done after a series of trials and error, of course, but this is absolutely possible. So in our experience, this type of microwave drying system can be used, and they are really efficient. And the only thing to do is to take particular attention on the design and on the maintenance of the system itself. So on my side, this is all I have. If you have questions, please let me know.
First of all, thank you. This has been a real wonderful talk. So I just checked if someone put in a question already. So it's not the case. Please feel free to ask questions. Your microphone should be open now.
Dear participants, if you would like to ask a question, please unmute yourself or type it in the chat.
Maybe I will start. On one of the last pages, you had mentioned a chamber design by 6 by 9 meters. Do you think there are limitations about it? What's your feeling? What's the biggest size of chamber you had so far, or the smallest one? Just to get a rough idea about what is the application possible in the field.
Okay, so this is a good question. Actually, this is a process-related question because what happens most of the time is that a customer already using traditional heating, so a customer which already has a cavity wants to start using microwave. So their approach is usually, we have this cavity, we want to apply microwave here. So there is no initial limitation on the cavity itself. We did cavities very big. So the biggest the cavity, the lowest is the risk of arching. And on the opposite, the smallest is the chamber. You have to be careful on the amount of power you are injecting, of course.
Right.
So it is always related to the maximum electrical field you have to put inside the chamber. But as I said, the moment we have the idea of the process itself, the quantity of material, and the ideal dimension of the process, we can simulate, for example, different type of waveguide entering, so that we can see in advance if there are critical parts inside the cavity which can result in an arching risk.
Mm-hmm.
So we did follow customer using, for example, 1 cubic meter cavities, using low power, let's say, but also we did follow customer with the very big cavities, as I said, 6 to 7 meters times 9 meters of diameter, rotating chamber, rotating cylinder. So this is really process related.
Yes, but then, for example, my next question will be, seems to be it's a little bit complicated and you need a lot of experience and knowledge, know-how. And are you or is Alta capable for the assisting to just get an excellent or good design, good cavity for all the approaches? Okay, yeah. Just before we had an existing chamber. Now maybe someone else want to do, okay, I've successfully done this process and now I want to do a new machine, and maybe we can avoid some mistakes. Exactly. You're able to give some support here?
Yeah, we can absolutely give support. So just to be clear, we are not manufacturing cavities because it is not our job. But what we do is to consider the existing desire or cavity of the customer. And we use an electromagnetic simulator. We have the capability to do it internally, but also with the help of the local university. What we do is to simulate the electromagnetic field distribution inside the geometry which the customer is looking for. And then, based on the first result, we apply an X number of sources of an amount of microwave power desired. So the moment we know the product we have to heat, its dielectric properties and the cavity design, the desired cavity design, we can put everything inside the model and figure out if there are critical parts. Of course, if everything is good, we can say to the customer, let's go ahead and do a test. Otherwise, if we see some critical part, we are doing a one-to-one with the customer, asking which part of the cavity can be modified, where we can enter with our microwaves, and we will start discussing the flexibility the customer has and we have in order to meet his requirement. Of course, in my point of view, the successful process design I saw were always trial and error, but were always following some specific steps. So pre-pilot stage, pilot stage, and then production. So it is probably not always feasible to do that, but to say that a process is working is one thing with microwave, then to scale up is another thing. So the moment you put a cup with the water inside the microwave oven and you say, hey, the water is boiling, it's okay. But the moment you have to do vacuum in a 1 cubic meter cavity is another topic. And the moment you are doing vacuum in a 10 cubic meter cavity is another topic. So, for example, we followed several customers doing these kind of steps, and the moment we had to move from the pilot to the production, there were a lot of undesired things which were not planned during the pre-pilot step. And so anytime you have to follow every detail to understand what to do. But this is where we can help, of course.
Thank you. So some question from the audience.
Yeah, question from my side, Francesco Marcus here. If a design for a process is ultimately a pair of microwave power and pressure, would it not be the case that in all cases that curve would more or less follow the Paschen curve? Which could be a first step or a first cornerstone for the process design? Yeah,
in general, I would say yes. So let's say that there are limitations ruled by pressure itself. So if this is what you're saying, so if we have a cavity and we need to reach a specific level of pressure, we need to know that we can't enter inside that cavity with too high electrical field. But this doesn't mean that we can't change the way we enter inside this cavity.
Yeah, sure.
So the pressure can't be, let's say, the air breakdown voltage can't be changed. This is something fixed, and you are right. So this has to be clear on the process side. The moment you want your water to be boiling at 46 degrees, you are roughly at 100 millibar. The moment you want the boiling temperature to be 30 degrees, you are well below. So yes. This is given. So this give me I wouldn't say limitation in terms of power, but limitation in terms of electrical field, which means I have to be very careful how to enter inside the cavity.
That's one thing, but for the end customer, the issue of costs for the pumping is probably at least as important as the microwave design issues.
Correct.
Water pumps for huge cavities are usually diffusion pumps, and those cost quite a bit, much more than the microwave itself. But that's another topic.
No, it is an important topic because, as you remember, one of the slides, there was basically a threshold of the pressure, and below that threshold, you are actually so there is a specific point where the air breakdown is very, very critical. Then, if you go very, very low with pressure, you can somehow help myself to give you more power in terms of microwave, but this will have a huge impact on pumping cost. So probably it is better to stay on the other side. So this has to be taken into consideration. Absolutely.
I understand.
Probably is worth to have a process which lasts a little bit longer, but avoid the risk of arching. And let me add, in my personal experience, the single, if a customer is looking for this kind of solution just to speed up the process, this is probably not the best thing to approach the microwave vacuum chamber.
Yeah.
Some more questions from the audience? Maybe then let me ask one more question. Before we talked a lot about the cavities and the design, everything, but one major part seems to be, for me at least, also the application itself. Which power at the beginning, how much power at the beginning, during the process, and at the end, for example, how to optimize everything. Is there some, of course, it will be dependent upon the product, which has to be dried. But I guess you also have some experience here.
Yeah, so I specifically, so let me be more precise. I focused on water because it was the simplest example when dealing about drying. But let's say that to make it simple, the product, any product, has dielectrical properties. So let's say that the moment we know the product, or at least the content of water we have to remove, we can estimate the power needed to take it out. This is also related to the speed you want to reach, because if you say I want to remove a total amount of liters in 2 days, it is different than saying I want to remove the same amount of water in 8 hours. So, right. Of course, this is a kind of formula we have to understand, to quickly understand how to dimension the system and the process. Okay. So there is a first approach with the customer saying I have a batch of this amount of material, and I need to remove all the water at least in X hours, and we do a very quick calculation on the power level required to do that. Yeah.
Okay, thank you. Some more questions, please.
Francesco, this is Bernd speaking. Good afternoon. I have a question. You know, we have a project ongoing with a customer in Germany for these honeycomb type ceramic units. And what I would like to better understand is the key topic here is we know the chamber design and all these things. How can we make sure or help to get the uniformity in the heating process around this chamber? You know, what are the trigger points? What can we do in order to get this really? You know how important it is to get a uniformity and an exact uniformed heating process for these honeycomb items.
So let me tell you this. There are several types of cavity, but in general thing, let's say you can divide them into two main cavity design. One is a resonant cavity, so it is something which is a cavity which is specifically designed to work at a specific frequency, which is not the case. Or you have multimodal cavities, like the domestic oven, like the big tank I was referring before, like the example you are referring to, where, just to make it simple, you have several microwave input sources. They are emitting microwave, and they are combining theirself and creating inside the chamber a lot of small hotspot, small or big hotspot. So in specific, this customer wants to reduce the hotspot, because if you have a product which is very precisely heated in one part and not heated in another part, this is not good. So what he wants is to have, as you say, the uniformity of the process. So there are different things or different ways to approach this. The first one, and this is what we did with that customer, was to do an electromagnetic simulation. Because with the electromagnetic simulation, you can see by adding or moving the position of the microwave entrance, if the hotspot are focused correctly on the product, or if we see hotspots in other area, and what is the overall uniformity of the electrical field. This is a first step which is mandatory because it gives you immediately an indication if the cavity and process is good enough. Then everything which comes after this is the experience of the customer, and with our help, of course, to help him maintain the uniformity during the process. But this is something the customer can experience only doing test. So by following what I said before, so let's say that one way is to heat the product and then stop the microwave and go down with the pressure, for example. This is helping to spread the heating not only by microwave but using the energy stored in the product itself. So there are different ways to reach that goal. For sure, the first step is to make a simulation.
How close do you think, or how big is the likelihood that with a positive simulation, which in this case it was positive, that we at the end find a way to tune the microwave power up to a level, in order to achieve the 100% requested on uniformity? Would you think that's pretty close? Means with our simulation, which was positive?
In my experience, yes. In my experience, the likelihood of a good process is strictly related to a successful simulation. Of course, there are things which are going beyond the simulation. So the precision of the chamber design, the precision of the electrical contacts, so a lot of different things. But the moment you start with a good simulation, then you just can improve.
Yeah, yeah. So maybe one last question from my side. How big is the influence of the final size of these honeycomb structured ceramic items? Because it could be, you know, it could be not it could be, it will be that they will put different size, different lots into the chamber, you know, which have different dimension.
Yeah, this can have an impact. This can have an impact because the moment you so let's look at the domestic oven, for example. So the domestic oven is designed to heat a cup of tea, but also something very thin. Yeah. So everything you put inside. And on average, let's say the final efficiency of the energy transfer is very low, because it is let's call it a general purpose cavity. So it depends on the difference of the product itself. If the products are very different in terms of dimensions, maybe it is better to perform different simulation, for example, to highlight if there can be some critical aspects or not. In that case, I do not remember very big differences. They were not treating very thin and very thick.
No, that's not the point. Just the general dimension. I mean, we could still talk to the customer and say, hey, is there a chance you try to put always the same size of ceramic, you know, items into one lot, if that's possible? Because the worst case I see would be he have to bring different size ceramic items into one batch. You know what I mean? No? That's the only difference here, which might have an influence.
So in that case, it is probably better to focus on the same dimension for everything.
Okay.
And then probably there will be the best scenario, the most probable scenario will be that for every dimension, you will have a different recipe.
Yeah, for example. No? Yeah. All right. Yeah. Okay, thanks, Francesco.
Sorry, had been mute. Some additional questions? So then let's thank Francesco for the very informative talk and a very nice talk with a lot of information for all of us. Just feel free either to contact MKS Instruments or to feel free to contact Francesco or his team for further information. You also can find some application notes on our MKS website regarding this topic. Yeah, thanks a lot, and I think see you next month for the next EU Tech Talk. Thanks a lot.
Thank you very much.
Thank you very much.
Bye-bye.
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 Thank you. Bye.
Bye.